SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We were discussing about the geochemical methods of prospecting, and we had some examples of the strategy for sampling, which and especially in reference to the soil geochemical survey, and how the results are interpreted or results are presented in terms of geochemical anomaly map. And now in the present situation, there are many improvements and many different ideas that have come up to this geochemical prospecting. Now there are ideas of sampling in terms of the regional or the whole country scale for preparation of regional geochemical anomaly maps, which can also be used during the reconnaissance purpose. Such kind of anomaly maps have been produced in large scale and already in process, and with the objective of having them as reference material even before a exploration program is planned during the reconnaissance stage itself. There are many different techniques like fluid inclusion also can be used as a tool for mineral exploration, when there are certain processes like boiling of the fluid or mixing of fluid sources which come out from the fluid inclusion microthermometric data and their proper interpretation. And since these processes are responsible in formation of ore bodies and enrichment of ores in different situations, they can also be effectively utilized for that. We are not able to discuss them in details. So today we will start discussing on the geophysical methods of prospecting. Before we start the discussion on geophysical methods of prospecting, let us get reminded us about the fact that we are not in a position, or we are not able to get into the details of the mathematical treatment or the detailed procedure of data reduction in geophysical methods proper. But as geologists, we could always have some appreciation, some basic ideas about the geophysical methods, which will be helpful for our general understanding and general guidance. So to begin with, let us first discuss about the magnetic methods of prospecting, and before we go to the little bit of details of magnetic methods and see any case study, we know that this any particular ore body, if we are planning to use a magnetic method, this magnetism or this magnetic field or whatever magnetism that is observed or that is measurable in a particular rock or any ore body, it is essentially divided into two parts, that is, or is coming from two contributions. One is the induced part, which is induced by the Earth's magnetic field, and that is how it depends on how exactly the Earth's magnetic field's orientation and the body that we are trying to measure with relative orientation to the Earth's magnetic field. And the other component comes from the remnant magnetism, which actually is the magnetism that is acquired by any magnetic material like a ferromagnetic or a diamagnetic material during the process of its formation for crystallizing from a melt, as we see in case of the sea floor basalt, which acquire the magnetism, and that magnetism or the polarity or the direction of the magnetic field is very much in accordance with the existing magnetic field of the earth. And the most of the process that we do, they measure the magnetic anomalies or magnetic properties of these the rocks and ores. So these come from these two contributions, which will be essentially the contribution coming from induction plus contribution coming from the remnant magnetism, and that is actually the total magnetic field that is or total polarity that is developed in that particular material. And essentially for any particular body of a rock or an ore, for its detectability by virtue of its magnetic property, it very much has to be the induction in the induced part of the magnetic property or magnetization has to be dominant, because this residual part is if the residual magnetism happens to be dominant, then it will be problematic for that particular body to show any magnetic signature. So, the magnetic response is directly proportional to the magnitude of magnetization and depends on the magnetic susceptibility. So, standard textbooks will always give the values of magnetic susceptibility of different minerals, and the rocks accordingly their values will be available based on the dominant constituent minerals. So, the magnetization is directly proportional to the volume of the concentration of these magnetic minerals, and the magnetic minerals are essentially the monoclinic pyrrhotite FeS, magnetite, which will be the most dominant one. If any particular rock has a very high magnetic susceptibility, it could be because of a high concentration or high proportion of magnetite, and then hematite will be less, but its gamma form, which is magnemite, could be still having more ferromagnetic characteristics than ilmenite and magnemite, which I just mentioned. So, the magnetism or the magnetic field, that is or the perturbation or the magnetic anomaly that will be observable, identifiable, will be basically coming out of this. So, the addition to proportion of magnetic minerals, the geometry and the depth of the ore body in relation to the direction of the earth's magnetic field is also an important criteria, and there are no fixed anomaly forms that can be regarded to give standard universal response to mineral deposits. So, complications may arise due to later metamorphism, deformation, remobilization. So, essentially what we would be looking for is that if there is an ore body and which has a high proportion of magnetic minerals like magnetite or monoclinic pyrrhotite, and in general some of the sulphide minerals will also have a higher magnetic susceptibility compared to common rock forming minerals, then we should be in a position to detect in the form of an anomaly when we measure the magnetic property of the rocks which are surrounding. This is an example of a very simple example which is taken from Asset & Khan 2000. So, here this magnetic survey which is conducted, supposing that our ore body or the material that we are trying to measure is a dipole, and it is oriented in parallel to the earth's field, and this is the measurement is being done in the equator region, and then we get an anomaly which will be of this shape. If the same measurement is done at a latitude which is 27 degree north, and in that the earth's field is inclined or oblique, then we get a anomaly pattern which will be more asymmetrical over here, and this is the anomaly pattern which we will be getting in the north pole, because the earth's magnetic field will be exactly vertical there. And the situation that can be imagined here, that what we measure is essentially an anomalous field which is measured in nanotesla unit, and this is an ore body where this dipole is oriented like this, north and south, and we can measure the field and the observed and the calculated field, and it will give us an anomaly on a local scale. I mean, if there is an ore body which is in the subsurface, and sometimes such kind of measurements of the magnetic field can be carried out by from an airborne magnetometer. These are done by some very well fabricated and well designed magnetometer like a proton precision magnetometer, where it can be airborne and can make a survey, and the magnetic anomaly could be plotted in the form of contours the way it has been shown here, and this contour interval being 100 nanotesla. So, essentially what it shows here, that there is a body, there is a magnetic anomaly, and it could be because of a body which is present somewhere in the subsurface exactly in this particular place where the magnetic anomaly is of the highest value. And the magnetic anomaly, because the ore bodies can always be approximated into different some simple shapes. For example, previously we considered a spherical shape, and if the ore body happens to be a shape like a dike, and here the it is a vertical sheet where it is a dike like body, and this field which is produced by the extended body is essentially due to the net poles that form on its surfaces, like the way it has been shown here. And if this happens to be at an angle to the north, here this is on the equator, this is in a place where it is oblique to the Earth's magnetic field, and here it is in the pole. So, you could get different types of magnetic signature. For example, here this body is trending east west, and here it is north south. So, in this case, a body which is trending north south and parallel to the Earth's magnetic field, we are not getting any anomaly. So, what in a qualitative sense what we get from these pictures is that whenever we have any magnetic body which is concealed below the cover, we take measurements of the magnetic property, magnetic inclination on anywhere on the Earth's surface, we should be getting many different types of patterns. Even in this case, the pattern which may be of a very similar body like a dike like this here may give different types of signals. And sometimes it also becomes important to know how exactly the where the body is and what is the depth, because one of the important parameters to measure is the depth of the ore body. So, these are very simple examples here. There is D1 and D2, there are three different depths of the same body being present, where this is a more superficial depth, D1 is the least, then D2 and D3 we could see the nature of the magnetic anomaly. And this gives a very simple formula, a very simple idea as to how to calculate the depth of the ore body, say for example, which is containing the magnetic minerals. Here this is the steepest part of the slope of the anomaly, that the curve that we are getting. So, if we draw a tangent here, so that becomes the line 1, and half of that tangent is line 2, and that half tangent line is drawn at points A and B, which are on the either side of the steepest part of the anomaly. And there are some very simple calculation procedure, very simple calculation scheme of giving the depth at which the body could be there. Depth is equal to D is equal to 1.6 of S. So, the S being the distance between these two lines, which are drawn from the half the slope points at point A and point B. So, with that little bit of a idea about how the bodies behave and their reflection in terms of the magnetic anomaly on any of the anomaly pattern that we get, which that tells us that it will depend on lot many factors, lot many disposition pattern, its relationship with the Earth's magnetic field, and the depth at which it is occurring, and so many other parameters. So, with that as a background, let us look at a case study of what could be the magnetic response of a volcanogenic massive sulphide deposit if we measure the magnetic property of that particular area. So, the assumption is that the ore body is tilted and eroded to expose a plan of a vertical section through the original center of the deposit and is located on a magnetic pole without any anisotropy due to inclination of the Earth's field. So, if that is the assumption, then the volcanogenic massive sulphide deposit geometry that we have seen, if you could just imagine that it is just tilted, so that the feeder the massive sulphide lens and the feeder stockwork feeder pipe with its alteration zone are all preserved, then we could think of there are many such possibilities which might be there. First, suppose that the VMS in this context, the first one, the A, it's basically the response is 0. Maybe that it has so happened that this particular VMS is lacking in all magnetic minerals, and in case A, which is nothing. In case B, we get a magnetic low here. So, the case in which the magnetic minerals are destroyed due to later hydrothermal activity. For example, whatever magnetite was there has been destroyed because of later hydrothermal activity, and they are converted to hematite or other kind of less magnetic in nature. It could be a case where it could be a situation like C, where that could be high and surrounded by a zone which is low. So, here the magnetic minerals like magnetite and pyrrhotite occurring at the top of the feeder pipe, and the lens is actually represented by this in the low. So, D could be that the base of a massive sulphide mineralization has a layer of magnetic minerals, for example, it is like Sullivan, or E is an extension of D where magnetic minerals occur throughout. So, giving this high signature of and let us say that how a porphyry copper deposit will be will actually show up on a magnetic anomaly that is measured on a particular this area where the ore body is occurring. Suppose this is the porphyry copper ore body, this is the propylitic alteration zone which is dominated by chlorite and epidote, and this is the potassic alteration zone, and here is the felsic porphyry, this is the phylic zone, and we know that the ore minerals will be accumulating over here. So, there could possibly be three situations which might come up. First one is the magnetite porphyry plus magnetite rich potassic zone. If this sometimes the potassic zone is magnetite rich by breakdown of the potash feldspar sorry the oxidation of the biotite to potash feldspar plus magnetite assemblage, then this zone could become magnetite rich and it will give you a positive magnetic anomaly is going up to 100 nanotesla. For example, if we look at the second situation where it might so happen that the magnetic porphyry and is the propylitic and the phylic zones being non-magnetic, and we can get situations which is noisy magnetics from inhomogeneous volcanics which will be surrounding, and we can get different types of such magnetic signature which is possible for the same porphyry type deposit where the three different situations is depicted. Say for example, there is a chromite body and it has been taken one example from one of the deposits. So, here this chromite body is actually surrounded by a serpentinite peridotite on top, and it gives an anomaly which is not that very sharp, but still we could sense the higher magnetic susceptibility of the chromite body compared to the serpentinized mafic rock. This is an example of a nickel sulphide ore body where the there is no contribution from the peridotite at depth, because what has happened here is this peridotite occurs just as just an inclusion on this body of the nickel sulphide ore. So, that is how it gives us a very prominent magnetic anomaly going to the order of 4000 nanotesla. But just if we have a situation where this sulphide body, this metal sulphide body, sulphide rich zone is included within the peridotite and also with some sediment on top of it, then this will give us an anomaly which will be different from the one which is shown here. So, these illustrations they show that the anomaly pattern that we get in many different situations could be different, and it will always, the interpretation could always be very I mean depending on information coming from any other source to confirm the actual nature of the disposition of this ore body and their relationship to the surrounding rock, by which in which case the anomalies could be reflected in many different ways. And just let us get some idea about the gravity methods, the way they are applied. This is a very simple diagram here showing that this the anomaly that we record here is because of the presence of a body which has a much higher density compared to the surrounding, measured in terms of grams per cc or kg per meter cube, whichever will be more comfortable with a gram per cc kind of value, which we know that how the values range in crustal rocks, and in many different situations the ores like a ultramafic ore or a chromite rich ore or any other ore which will have a very perceptible difference in the density with the surrounding. For example, these three, one with a spherical body which is lying at a deeper part, or a lanceolate body which is lying at a little shallower, or just a flat lying kind of a vein which is lying just near to the very surface, they all might give the similar type of a gravity anomaly in terms of the milligal that this gravity anomaly is produced. And this diagram also gives a very good idea that the situation here there is a granite which is about 2.6 megagram per meter cube, means 2600 kilogram per meter cube of rock, and where the basement is 2.7 megagram per meter cube, and a shale. So, here the situation where a body of granite is enclosed within shale and basement, or here there is a limestone which is basically occurring along with the basement and the same shale, will give exactly the identical kind of a gravity signature if we take the gravity measurement, the gravity anomaly. And what we are not exactly discussing here is that the process is definitely very elaborate, and these data that are taken by instruments like a gravimeter or that we take in the field or in the airborne gravimeter, there the data are acquired and they are subjected to a lot of corrections which are essential before we can get the data on which the interpretations could be made. And such kind of gravity anomaly map could be plotted on the ground, a simple type of profile, or once a larger area is covered, then based on the gravity anomaly measured in terms of milligal, it could be a similar gravity anomaly map, a regional scale gravity anomaly map could be produced. And here the depth rule also applies. So, here for example, if it depending on what is the kind of shape of the body that we presume, if it is a spherical shape, then so this peak essentially we can always take the peak at a half height and the half width at half height. So, this is the width at half height, and here it could be a simple formula like the depth at which depth to the center essentially lies this just about 1.3 into the half widths. In this case it is just the half width, and in the case like this where it is a dike like body that we are showing here, if we presume that the ore body which is in a higher density compared to the surrounding is having has a shape of a dike, then here the depth to which the dike could be occurring is 0.7 of half width. And here it is interesting that if we consider any irregular shaped body, which is more likely the case in nature, there the depth is usually found out by the slope, that is the change in the gravity anomaly, this slope on this side with distance dg by dx is multiplied by the del g max, that is the maximum anomaly that we are getting here. So, that will be less than or equal to 0.86 into this del g max divided by the slope that we get as the del g by del x. And in most of the cases when we will be seeing the case studies also, that these always will be give us some very basic idea whenever we are discussing application of a magnetic method or a gravity method for exploration of any particular ore body and looking at the case history. This is an electrical method. As we all know that this electrical method are more applicable for example, most of the cases we have situations like there are crustal material, the rocks, different types of rocks, the rocks could be of different their porosity, permeability characteristics could be different, there are different types of water bearing horizon, there could be dry rocks or could be fluid filled rocks. So, they will be differing in their resistivity, which is we can put as rho 1, as rho 2 and rho 3, and this is what we are basically putting, this rho is the resistivity, and as we will be seeing here, amongst the electrical method we will only be considering the one which is the resistivity sounding or the resistivity profiling, which is mostly used. And as I just showed that most of these cases for situations like detecting a water bearing horizon for groundwater survey, this kind of arrangement, this kind of device is used, where there are current electrodes and potential electrodes, and when the current is applied, the potential difference is measured, and there are different types of configurations, like this distance between the potential electrode and the current electrode. Either they could remain as one is fixed and one the other one to be moving, or the all four could be moving apart, moving away from each other, and that is by allowing the current to flow deep to deeper and deeper region of the different layers. And we get when we plot the logarithmic log scale on the logarithmic of log of the resistivity, apparent resistivity versus the log of the array spacing, we get different types of curves from which we interpret in terms of different layers of different resistivity that is there below the surface. So, these kind of resistivity sounding are very widely or very regularly applied for the exploration of groundwater, which are essentially the layers more or less to be horizontal or to parallel with the earth surface, and such kind of situations. And here also just for the sake of understanding, we know that what we are measuring here is the apparent resistivity, because it is not since it is a heterogeneous material consisting of different types of mineral grains in a rock matrix or water, or sometimes even the water will be of different salinity, which will vary in their electrical conductivity, and that is how changing the resistivity. So, what is measured essentially is a apparent resistivity, and that apparent resistivity is when it is plotted with the log of the array spacing, and these kind of. So, these are very standard procedures which are available to interpretation of these graphs in terms of water bearing horizons, and there are much more developed computer codes also these days available, which does the job for us. But essentially the situation is that the ore bodies which are of our interest will very in majority of the cases will not be like in very rare exceptional cases where they are very stratiform and very conformable to the sedimentary strata, or such kind of a situation where they are occurring. But in most other cases, like in vein types of deposits or bodies which are oblique to the sedimentary strata, or later on they are tilted or deformed, and they are present in shape which will be more depicted by the situation which is here, like this is rho 1 and rho 1, and our body of interest is something which is like rho 2 over here. So, there it becomes more challenging, it definitely requires a little bit more of elaborate procedure to actually identify. And here our objective is not just to detect the presence of the low resistive or higher conducting body which is an ore body, but also we need to know the shape, approximate shape in which this particular ore body is occurring underneath, because that will be the most crucial aspect of our survey, because what we intend to do finally is to reconstruct the shape of the ore body in the subsurface. So, there is a method which generally is applied in many of the case histories of discovery of mineral deposits by use of electrical method which is encountered. This is known as a mise a la masse method, in which instead of the electrodes, the current and the potential electrodes moving or being moved away from each other on regular intervals, what is done here, that the potential electrode is fixed on one of the points corresponding to the exposure, or wherever we detect that there is such kind of for example, by a geochemical survey or any other method, we get to know that there is an ore body which is below this particular point. So, we could place our potential electrode there, and through series of drill holes we the current electrodes are also inserted, and the resistivity profiling is done in a way, and these are the lines which are representing the lines of equal resistivity, and that is how the shape of the ore body could be very much well approximated by such kind of method, which is known as a mise a la masse method, which a application of this we will be seeing in one of our case studies. and situations corresponding to this are something which is a little improved method, and it is something which is called as an electrical imaging in case the body is very elongated like the one which is shown here. And some such situations are very common, even a situation which could be a kimberlitic pipe, or it could be a brecciated ore bearing zone, or it could be a deep seated fracture filled with quartz reef kind of mineralization like Malanskan type of mineralization which we have discussed. So, here the profiling is done on regular intervals in 2 dimensions over the entire area, and what is reconstructed is something like a pseudo section, and these values representing the different resistivity value regions, and from which this kind of geological section could be reconstructed. So, the other type of electrical methods that is regularly used for detection of the sulphide mineral bodies is the induced polarization method, which is used for disseminated sulphide body, because induced polarization takes the help of the principle that if we are applying, it is more like the same way that the resistivity method by which we apply current to flow through the surface. When the current applies, then there is generation of this the creation of polarity within the minerals, sulphide conducting minerals. The only exception to that is fullerite, and then if we stop full flowing of the current, then there are some residual potential which remains there and which then gradually decays, and that is measured, and that is the induced polarization method, which is mostly applied to situations where there are a disseminated type of ore body. But situations like this where we have an ore body which is a concentrated like a vein, or any kind of a situation like even a massive sulphide vein where the concentration of the ore minerals are high. So, here we use methods which are called the self potential method. In this method, there is nothing or no current is flown to the surface. It is just as it itself behaves like a polarity is developed in the different part of the ore body as shown here as a negative and the positive side, and current flows through this from a closed circuit, and that current could be measured by using the potential difference could be measured by using a voltmeter, and so this gives an idea. So, this is how the cell potential method survey is done. Just one needs only a moving electrode and the device to measure the potential, and this cell potential, that is the data that is acquired, can also be plotted in the form of contours, and this is one example taken from one of the deposits. This is an SP anomaly map which can be prepared, and by that we can always pinpoint the higher anomalous zone as shown here in negative value. So, these will be indicating the presence of the sulphide ore body. So, we will continue with our discussion of some of the case studies where the methods that we have discussed, like the geochemical method, the sampling and the production of or the generation of the geochemical anomaly map, or looking through the series of geophysical methods like a magnetic method or a gravity method or an electrical methods like resistivity. So, some of the case studies we can see how this combined use of all these methods result in discovery of mineral deposits. We will continue our discussion. Thank you.